So this lecture is going to be about the finite affine plane constructions, and I'm going to go ahead and do problems related to that from old final exams. So this is an example of a 7 by 7 array. So this would be when we're working at an affine plane of order 7 and doing modulo 7 arithmetic. And I've circled 2 points here and here. And we want to go ahead and circle in the other points that are on this line. So let me go ahead and make those clear. We could figure out what the congruence is for this and figure out what the equation of the line is and then just circle the points. But let's just go over 3 and up 1. 1, 2, 3. This would be a point also. 1, 2, 3 and up 1. This will be a point. 1, 2, 3 and up 1. This will be a point. 1, 2, 3 and up 1. This will be a point. 1, 2, 3 and up 1. This will be a point. And we can stop there. In a 7 by 7 array of points working mod 7, we're going to have exactly 7 points. So an affine plane of order 7 has 7 points on a line. So those are the 7 points, and that would finish this problem. Here, I'm just asking to draw an affine plane of order 3. So we just want to go ahead and draw all the points and lines. So let's begin with the 3 by 3 array, the 9 points. I'll just draw them in there, and I've drawn in some of the lines as well, the horizontal lines and the vertical lines. So those are slope 0 and undefined, or slope infinity if you want. And what we need to do is to draw in the ones with slope 1 and the slope 2. So let me draw on the lines with slope 1 first. So this would be one of the lines with slope 1. I have another line going through these 2 points, and then this would be the same as this point. So going through these 3 points. And then I have one going through these 2 points and this point. So I'll draw in that line as well. And so those are the ones with slope 1. And we have lines with slope 2 we want to draw. But remember, 2 is the same thing as minus 1 mod 3. So it's probably easier to go ahead and draw in a line going through these 3 points using slope negative 1. So I'll do that. And then we have another one going through these 2 points, and that would be this point. And this last one would go through these 2 points, and that would be the same as this point. So it's going to go through this one. And I drew it that way. So anyway, so it goes through those 3 points, and we have our lines. We have all the lines, because we had 3 with undefined slope, 3 with slope 0, 3 with slope 1, and then the 3 with slope negative 1 that we ended with. So those are all the possibilities for the slopes and the lines, and that's going to be all the lines and all the points. So that would be my model then for a finite affine plane of order 3. In this problem, we're trying to see where 2 lines, y is equal to 20x plus 17 mod 41, and y is equal to 23x plus 19 modulo 41, intersect. 2 lines in an affine plane of order 41 don't always intersect. You can have parallel lines, but these 2 lines intersect, and we're trying to find the point of intersection. Now, we want to take A and B between 0 and 40 usually, so this is a typo. We want to go from 0 to 40. There's no problem with having a 41 there, but we should be able to get A and B between 0 and 40. So we do this like regular algebra. We have 2 equations like this. What we would do, you will have y being something here and y being something here. Well, these 2 have to be the same then. So we set those 2 congruent to each other, modulo 41 in this case. And then we just solve for x. That would be the next thing you would do with the algebra. You subtract 20x from both sides and maybe subtract 19 from both sides. So you have 3x's minus 2. Now, minus 2, if I add 41 to that, it's the same thing as 39. So is it okay to divide by 3 when you're doing modular arithmetic? Well, if you're working a modulo of prime like we are, and whenever we're doing finite projective planes of order of prime, we're going to be working modulo of prime, then you can divide by something as long as it's not 0 modulo that prime. So what does 0 mean modulo 41? You don't want to divide by 0. You don't want to divide by 41. You don't want to divide by minus 41 or 82. You don't want to divide by anything that's 0 modulo 41. But you can divide by other things. So it's okay to divide by 3 on both sides of this. And you can see then we'll have that x is 13 modulo 41. So x is 13 modulo 41. And again, dividing by 3 on both sides is okay, not just because 41 doesn't divide 3, but also because 41 is prime. So that's something you can do when you have a prime modulus. So we have what x is, so that tells us then what a is, because what we were looking at is what happens if x and y satisfy both of these, and we got that x had to be 13. So a is going to be 13. So next we want to find b. And again, this is regular algebra. How would you do that after you got that x was 13? Well, you go back to one of these equations, or congruences in this case, and figure out what y has to be. So I can plug in 13 here or here. I think I'd prefer to multiply by 20. So I'll plug it into the first congruence there. And y is going to be 20 times 13 plus 17. So 260 plus 17 is 277. And then you want to subtract some 41s from this. So you can see 6 times 41 is 246. So if I just subtract 246 from this, I'll have 31. So y is going to be 31 modulo 41. X is 13 modulo 41. And so we get what our point is. The a has to be 13 and the b has to be 31. So that gives me the point of intersection of these two lines. So that finishes that problem. Now let me go to this 1993 question. Here we're given the description of how we construct a finite affine plane of order n. And this worked when n was a prime, but I'm describing it in general. We take a and b, the points to be with the coordinates a and b between 0 and n minus 1. We take our lines to look like y is congruent to mx plus k, where m and k are between 0 and n minus 1. And also x is congruent to c modulo n, where c is between 0 and n minus 1. So those are giving us n squared points and n squared plus n lines. Now what we want to do in this problem is suppose that n is 4 and say what goes wrong. And this construction worked when n was a prime. It doesn't work when n equals 4, and your task here as a student would be to try to find an axiom that doesn't hold when we look at these n squared points when n is 4, 16 points, and these 16 plus 4, 20 lines. So let me remind you what the axioms of the affine plane is. And one is that there exist at least 4 points, no 3 of which are collinear. And when n equals 4, this one's going to say there exists at least one line with exactly 4 points on it. And here we have that if you take any two distinct points, there's exactly one line passing through them. And the last one is if you have a line L and a point P not on L, then there's exactly one line that's parallel to L that passes through P. So those are our 4 axioms for a finite affine plane of order n. And what we want to do is to consider this with n equal to 4. So again, we had n squared, 16 points. And for our construction, we want to go ahead and make an array out of this, a 4 by 4 array. And so we can draw our lines and see what happens. Now, I actually don't want to draw on all the lines. I want to be a little bit smart about this. I want to draw on a line with slope 2. Now, why slope 2? Well, 2 I know is going to be somewhat problematic, and the reason is that 2 behaves differently mod 4 than it does for odd primes. If I take a prime 3, 2 has an inverse. There's something I can multiply by 2 that gives me 1 modulo 3. So 2 times 2 is 1 modulo 3. If I look mod 5, 2 times 3 is 1 modulo 5. If I look mod 7, 2 times 4 is 1 modulo 7. When I look mod 4, there isn't a nice inverse. There isn't any inverse for 2. 2 times something is going to be even. Even numbers mod 4 are 2 or 0 mod 4. So there isn't anything I can multiply by 2 to get 1 mod 4. So 2 is a little bit different mod 4, and so what I'm going to do is try to take advantage of that by looking at a line with slope 2 and see what happens. Now, which line I take with slope 2, well, I can move it up and down. It probably won't affect what we're trying to get at here, so I'm just going to make it go through the origin. So it has slope 2 and passing through the origin. So this will be a point on it, and then if I want to have slope 2, this will be a point on it. So now I want to go over 1 and up 2. This will be a point on it. Over 1 and up 2. This will be a point on it. And it's only going to have 4 points. We only have 4 points on a line in our construction. And in fact, we should question a little bit doing what we did to get these points, because the definition of lines again from the previous slide are going to be y is congruent to mx plus k, or x is congruent to c modulo 4. So what is the line here? The line here is the line with slope 2 passing through the origin. We want to use y is congruent to 2x mod 4. So y is congruent to 2x mod 4. When x is 0, we get the point 0, 0. Y is going to be 2 times 0. When x is 1, we get the point 1, 2. 2 times 1 will be 2. When x is 2, we get the point, let's see, y is going to be 2 times 2, or 4, and that's 0 mod 4. So that's why we're at 0 here for the y. So when x is 2, y is 0. When x is 3, we're going to have 2 times 3, which is 6. That's 2 mod 4. So y is going to be 2 mod 4, and we'll be at the point 3, comma 2. So that gives us the points for that line, y is congruent to 2x mod 4. Now, the next thing to think about is what would be a good line to use along with this line to say something maybe doesn't look right for this model. And what I'm going to do is to take a line that intersects this other line in 2 places. So I'm going to take this line or this line here, and I'll just take this line down here, and I'm just going to circle these points then in green. So this will be the green line where I have green circled points. So what's the congruence here? It's y is congruent to 0 mod 4. If I take any x, any value of x between 0 and 3, y is 0 mod 4, and we'll get the point, whatever that value of x is, comma 0. So that's the line going through those points. And now we can see that this line in green and this line that with points circled in blue intersect in 2 points. That is not something we had before. Let's check the axioms. Does that cause any problems? Well, the first axiom was there exist at least 4 points, no 3 of which are collinear. That doesn't seem to be too relevant to this picture. There exists at least one line with exactly 4 points on it. Well, that's relevant. We have lines with exactly 4 points on it, but that just means axiom A2 does hold. Given 2 distinct points, there's exactly one line that they both lie on. There we have it. We have 2 points that are distinct, and we have 2 lines passing through them, the blue one and the green one. So this is not true. There is not exactly one line passing through these 2 points. And again, those 2 lines we drew are distinct lines, because lines on the previous slide, the n squared plus n lines, the 20 lines mod 4, were defined to be of the form y is congruent to mx plus k and x congruent to c mod 4. So y being 2x mod 4 for this is a different line than y being 0 mod 4. So we have two lines passing through these 2 points in our model, and that's going to mean that this model is not a model that satisfies axiom A3. So axiom A3, not 3 here, does not hold. What about axiom A4? Well, here also, this picture we have shows axiom A4 doesn't hold if you look at the right thing here. What I'm going to do is look at the line y is congruent to 3 mod 4. It passes through these 4 points. Y is congruent to 3 mod 4. So let's say that's our line L, and I can use one of these points that were problematic before, say the origin for P. And according to axiom A4, if this is L and this is P, there can only be one line passing through P that's parallel to L. Well, both the blue line passing through these circled blue points passes through this point, and so does the green line. But notice that neither of those lines have a point in common with the line L that we described, y is congruent to 3 mod 4. So neither of those two lines intersected this line L. So both the blue line and the green line are parallel to L because they have no points in common with L. And both of them pass through this point. So axiom A4 would not be correct because if I take my L that I described and the point P being the origin, then there's not exactly one, there's two lines passing through P that are parallel to L. So axiom A4 does not hold as well, and again, that should be an A4. Axiom A4 does not hold. And so for this problem, either the answer could have been axiom A3 or axiom A4, because I just asked for one axiom that doesn't hold, but neither of those hold. For this 1995 final exam question, we have 2 points in an affine plane. And what you should know is that if you're given 2 points in an affine plane, there's a unique line that passes through those 2 points. And so we should be able to find a line that passes through those 2 points. So what we're trying to do is figure out what M and K have to be this line passing through these 2 points. So M and K we can take between 0 and 16 since we're working mod 17. So we'll do that. And just like an earlier problem we looked at in this lecture, we want to do this like we would with regular algebra. So if I asked you for the equation of the line passing through these 2 points, the first thing you should do is find the slope. So the slope is 11 minus 6 over 8 minus 14, the difference in the y's over the difference in the x's. So we're going to have 5 over minus 6, or minus 5/6. And we don't want to work with fractions in modular arithmetic, so I will say this is m, and rewrite this as 6m is congruent to minus 5. So 6m is congruent to minus 5 mod 17. I want to know what m is. I'm trying to find the slope. You could multiply both sides by 3. 3 times 6 will be 1 mod 17. And that would tell you what m is. But I'm going to go ahead and do this the way I did before. I'm just going to add 17 to this minus 5 to take 6m, to say that 6m is 12 modulo 17. So 17 does not divide 6. 17 is a prime, so I can divide by 6 on both sides. And this will give me that m is 2 modulo 17. Okay, so we have m is 2 modulo 17. Now we want to find k. So we have y is 2x plus k, but we have points. So we just plug in one of the points to figure out what k is. This might have been an easier point to plug in, but I'm just going to plug in this point. So that's going to give me 6 is 2 times 14 plus k. So we have this congruence modulo 17. This will be minus 28. We bring the 28 over. We have k is 6 minus 28, or minus 22 modulo 17. I want to add 17 to this, so add 34 or 17 twice, and we'll get 12 for what k is. So we have m is 2 modulo 17, and k is 12 modulo 17. So that tells us what this is. We have 2x plus 12. And so the answer to this problem would be that y is congruent to 2x plus 12 modulo 17. So I'm going to finish this lecture there.